Hello everyone, in this tutorial video I'd like to explain how to evaluate limits of functions that are not well behaved at the point specified. For example, if we are asked to evaluate the limit as x approaches 2 of x squared plus 4x minus 12 all over x squared minus 2x, we would see if we tried just evaluating the function directly, we would get 2 squared is 4, 4 minus 2 times 2 is 4 minus 4, 0 in the denominator. So you'll have to figure out a different type of technique to compute the limit. We can see, however, if we factor both the numerator and denominator, they have a common factor of x minus 2, so we can cancel them out, and we get x plus 6 over x for our simplified answer. And now, when we plug in 2 to this fraction, we get 2 plus 6 is 8 over 2 equals 4, so the limit is 4 from this computation. You may be wondering to yourself how it is possible to simplify a limit like this, given that it seems to be two entirely different functions that are not related to each other. The answer to that is to notice that they actually are technically the same function. The only place where it's different is where the denominator is 0, so for every x except 2. And we remember from learning the conceptual definition of the limit that the limit is only used to estimate what is happening around a spot in the function. It never, and I mean never, gives you the actual literal value. The formal term for 0 over 0, what we got initially trying it, is called an indeterminate form, and this is because 0 over something is normally 0, but something over 0 doesn't exist. So these two rules compete, and it is not clear which one will win. Hence, it is called an indeterminate form because you cannot determine what the value actually is. If we have this limit, we would see plugging in the limit value requested 0 would not work, because you also get 0 divided by 0. But what you can do is expand the squared part by multiplying -3 plus h by itself, then distributing the 2 across the expansion. We see that the two constants in this function, 18 and -18, cancel each other out, and so we can now factor out h from everything. So the simplified form becomes -12 plus 2h, and plugging in h equals 0 directly is -12 plus 0 equals -12, so that is the finite value of the limit. Again, it is important to emphasize the limit has a finite value, even though the function is indeterminate, because the limit is only an approximation, it is not the literal value of the function. If we are asked to evaluate a piecewise function such as this, at the point where the graph breaks into the two separate graphs, we would take the left-hand limit, which is y squared plus 5, and we evaluate it directly as 9. Similarly, the right-hand limit is 1 minus 3 times y, which evaluates to 7. We see, because these two limits do not agree, the normal limit does not exist. So that is our final answer for attempting to compute the limit. However, if we change the right-hand value to 3 minus 3 times y, we would see it evaluates to 9, just like the left-hand limit. So in this case, the normal limit does have a finite value, which is 9. Before we conclude our discussion on computing limits that are not well behaved, there is one last special type of limit we would like to look at, which is that if function 1 is lesser than or equal to function 2 for every x from point A to point B, and we know there is a value c between A and B, then it should follow that the limit of function 1 at point C is lesser than or equal to the limit of function 2 at point C, given that the limit of function 1 is always lesser than or equal to the limit of function 2 throughout the entire interval, regardless of whether we are studying point C or another point. If we also make the assumption that both of these functions are well behaved, so that the limit is always exactly equal to the literal definition of the function at that point. It should follow that function 1 at point C is lesser than or equal to function 2 at point C, which are exactly equal to the limits at those points because we assumed both functions were well behaved. So now we can create a third function, h of x, which is in between these two functions, and state that if the limit of these two functions are equal to each other and also equal to a finite value, then it follows the function of the middle value, h, must also equal that finite value. The formal term for this is the Squeeze Theorem, also known as the sandwich theorem or pinching theorem, owing to how the middle function is squeezed, pinched, or sandwiched between the top and bottom functions. Note too, because of how limits work, the middle function does not actually have to exist at the point we are evaluating. Only the limit has to exist. So, an application of the Squeeze theorem is, if we are asked to evaluate the limit of x squared times cosine of 1 over x as x approaches 0, we would do this by first noticing the cosine function always returns a value between -1 and 1 by definition of cosine, and the cosine function does not care about what the input or argument is. It will always give you the same two minimum and maximum values. But for the purposes of our problem, we will specify the input is 1 over x. And now we multiply everything in the inequality by x squared to get everything in terms of the function we want to evaluate. And we see the limit as x approaches 0 of negative x squared is 0. And the limit as x approaches 0 of positive x squared is also 0. In conclusion, because our function is between 0 and 0, it must also be 0 logically. So we have a finite limit of 0. We can prove this by showing the graph of these functions, and seeing that x equals 0, the original function is smushed right between x squared and negative x squared. The Squeeze theorem only works for very, very specific limits, i.e. limits that you can squeeze or sandwich between two finite values that are equal to each other, which is not always possible. In the next tutorial video, we will investigate limits that return a value of infinity or negative infinity and how they work, provided that infinity and negative infinity are normally not acceptable values in the study of traditional math such as arithmetic. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.